Hey everybody, hope you guys are doing okay during this US election week, or maybe even US election month. We don't know. Votes are still being counted as I'm speaking to you today at the end of November 4th. So today, I'll be talking about kind of a sensitive topic, and that's because I wanted to pick an application that was sufficiently complex for us to sort of dive a little bit deeper into point pattern models. I was going between two sort of areas. I'm big on using statistics to do important work. And so, forest fires are important, and missing migrants are important. So I think I'm drawn to applications where not a lot has been done. And I haven't seen a ton where this particular data set has been analyzed. I've seen a ton, however, on the application of point pattern modeling to forest fire analysis. So with that in mind, sort of be aware that we'll be talking about fatal incidents of migrants. There will be no images of migrants. We'll be doing statistics after all. There'll be images of statistical models, but this is a sensitive topic area. And so we just wanted to sort of get that out there. With that, our data set comes to us from the Missing Migrants project. They keep track of fatal incidents involving, in the process of migration. And this involves, as we see here, migrants, refugees, and asylum seekers who have died or gone missing in the process of migration. So that, you guys can go to the website and find out everybody who that includes and excludes. This is a publicly accessible website. The data are as of October 27th. So I've been working on this for a little while now. Wanted to make sure I give it its due diligence. Like I said, it's a complicated data set to analyze, and that's what I'm hoping to convey in this lecture about how to analyze complicated things. So with that, we'll be focusing on an aggregate of all data that is available on this website, which is 2014 through 2019, which includes over 2,000 fatal cases. I am focusing on an area that I know a little bit about, which is close to home. I'm specifically excluding the Caribbean. Point pattern modeling over the sea and land should give you a lot of pause, because that's a complicated observation window to partition. So I am focusing on land. Specifically, by the way, that's why I'm not looking at the Mediterranean, because there it's quite divided between incidents on land and incidents in the Mediterranean Sea. So we'll be focusing on the southern US and Central America. So with that, let me flip into R. This map is hopefully more informative when it is interactive for us. So let's start with that. So I've posted this out on our website. And at this point, we're going to be drawing on a lot of things we've learned in the class already, not the least of which is projecting our data. We have collected data on a very large area. And so it's very important to keep our distance units in mind, our geography in mind, and so forth. So with that, I'm going to read the data set. And right here, lines 19 and 20, I transform it into a spatial object. I have to first set the latitude, longitude as a coordinate reference system. And then using this pipe, you will be seeing this little operator quite a bit in this particular lecture, because it's just really streamlined to take a set of data and sort of transform it in one fell swoop, so to speak. So here I take my data, cast it as a spatial object with the latitude, longitude as its coordinate reference system, and then immediately transform it using universal translocator, zone 13W. By the way, zone 13W, again, this is supposed to be an intermediate or even difficult analysis task. We're definitely crossing multiple UTM zones. But I picked one, zone 13W, that pretty much cuts my observation window in half. I probably could have played around that if I was, if my best friend was a cartographer, they would be able to recommend perhaps a better approach, but I didn't want to deal with decimal degrees. I wanted to certainly deal with meters and kilometers. And so I picked a UTM zone that was sort of in the middle of my observation window, which happens to be zone 13W. With that in mind, I'm going to project it and then make a quick map. Notice I'm making an interactive map, and I am not making a choropleth map. This is not a choropleth map going all the way back to the first unit of the semester. This is simply a dot map because I am recording nothing more than where these fatal incidents were recorded. For a little bit easier read, I'm going to just overlay the political boundaries. And so we take a look that this particular data set covers Central America, so from the border of Panama and, ooh, what country is this? And I call myself, looks like Colombia. Call myself a spatial statistician. Looks like we're covering everything from the border of, southern border of Panama, all the way to the US-Mexico border. But also, if you look, we're definitely stretching quite a bit away from the border, where we're seeing migrant deaths pretty deep into Texas, fairly deep into New Mexico, fairly deep into California and Arizona. So with that, we want to now decide what might be a reasonable observation window. And that is admittedly hard to do for this particular data set. You will notice, of course, that most of the cases, most of the migrant fatalities are clustered around the border, and specifically the US-Mexico border. That's not particularly surprising. So we definitely want to include parts of the US and parts of Mexico, but not just Mexico. There are migrant deaths in Guatemala, in El Salvador, in Nicaragua, in Panama, and Costa Rica. So I propose, and this is not the only way to do it, but I propose that we choose the US border states, right? We have California, Arizona, New Mexico, and Texas, and the entirety of the border states, as well as our Central American countries, Mexico, Guatemala, Honduras, Nicaragua, Costa Rica, and Panama. Again, we are assuming that a migrant death could have occurred everywhere inside of our observation window. So we're saying, by including all of this area, that we could have observed, in theory, a migrant death in San Francisco. We could have observed, in theory, a migrant death in Flagstaff, Arizona, in Lubbock, Texas, right over here somewhere, okay? Now, could I have gone a different route? Of course, I could have looked at my data and said, it's highly unlikely that migrant deaths occur past some buffer of the US-Mexico border. But then we need to decide what buffer to use. Would it be like a 100-kilometer buffer? Would it be a 500-kilometer buffer? Would I use just the bordering counties? Would I use the 2 bordering counties? And we know enough about point pattern models now to know that that would affect the analysis, because our under the hood of point pattern models says we're going to fill our space with dummy points to represent the absence of data. And then we're going to combine that with our point pattern to represent the presence of data. So although I don't observe any migrant deaths in Northern California, I thought that was going to show there. I don't observe any migrant deaths in Northern California. I will have to fill that space with dummy points and perform modeling for why there are not deaths in Northern California. But there definitely are deaths in Central Texas. So preview, distance from the border is absolutely positively a covariate. Okay. We're going to continue to make sure that everything is projected the same way. Remember that this package sort of overlays the observation window and the data on top of it. And then we have to match up all of our covariates that are defined across the entire observation window. So we have to be super careful to make sure everything is projected the same way. If we project one thing in latitude, longitude, and another thing in UTM meters, or we accidentally make this zone 16W, it is not going to match up. The R package is going to get very upset with you and start yelling. Other considerations. Spent a long time thinking about this observation window, by the way, because what about the migrants who died offshore? So if we kind of look in a little closer, we see that there are sort of these linear patterns. Perhaps it's easier to sort of, whether there was a road there, whether there was a railroad there, it's easier, it's a valley, it's easier to sort of walk, it's easier to pick up sort of transport, but there's definitely some migrants who likely drowned. For example, these points here. We can actually click on them and it will tell us a few things, the ID of that particular incident, its region, the date it occurred, month, and the cause of death is drowning. It also tells us the quality of the source. If we wanted to, at this point, we could filter our data to only include points of a certain quality source. So if I go ahead and use the polygons that I have here, you might imagine that I'm actually going to exclude all migrants who have drowned. So, what would be a way around it? Again, think of a buffer of a certain number of kilometers and put that buffer around the shore. But I did not do that because I didn't want to think of what buffer to use and think of a reasonable buffer. Of course, the observation window changes again if we only consider the border counties. The relationships between the different covariates change, so on and so forth. So the other sort of thing I wanted to relay for this kind of analysis, the statistical modeling is almost the easy part. It's setting up and collecting all the different data and reprojecting everything and keeping everything projected in the same set of units. That's the hard part. The modeling is just a Poisson, generalized linear model. So you will see a lot of setup and you will see relatively quick analysis. But of course, we want to understand how that setup occurs because the analysis cannot happen without it. So with that, I'm going to collect my border states. You can see I'm using the map function there. I'm collecting my border states. And then I'm collecting, using, by the way, the same map function, just not the state database, the world database. I'm collecting my Central American countries together. I'm now going to convert everything into a spatial polygon. I'm going to first assign the lat-long coordinate reference system. And then on line 46, I am reprojecting everything using the UTM zone 13 into meters. And I am giving a 50-meter buffer around my polygons. And this buffer will help me execute the join. So I make my sort of US side of the window first. I make my Central American side of the window next. And then I put a slight buffer in there just to make sure there's not a weird sort of space in between, just in case I record some polygons at a better resolution than other polygons. So this is what this buffer does. And the units of the buffer are, of course, meters because of this projection. So it just kind of helps me overlay the two parts of my observation window together. All right, all of that runs, and of course this code is uploaded. And finally, I'm using this ST union. And as you might imagine, it combines different polygon collections together. And finally, a plot that produces this graphic for us. Okay, looks like I have my observation window. I now have to, of course, remake it as what StatStat wants as its observation window. And I'm going to rescale it into kilometers. Now, this is a huge area. I didn't want to deal with teeny tiny intensity numbers, because if I didn't rescale it into kilometers, remember, intensity is the expected number of events per unit area. It would be the expected number of migrant deaths in a square meter area. A square meter area is right here in front of me. That's a square meter area. How many migrant deaths would be immediately around me? That's kind of a silly metric. That's why on line 64, I go ahead and rescale my observation window into kilometers. And just to show that we're working with a huge area, that's not the area of that. 4.25 kilometers, that is not the area of the window I'm looking at, but this looks like a much more reasonable area of the window that I'm looking at. That looks like 4,258,000 square kilometers. That's our space that we're trying to model. Now remember, we are going to model empty space. That's how these models are fit. Okay. I'm going to now rescale my coordinates from meters easting and meters northing into kilometers easting and kilometers northing. Finally, make a point pattern object. Okay. So at this point, we have the following warning messages. We have 94 points that were rejected as lying outside the specified window. So I know that there are some drowning deaths that are going to be rejected because they occurred just offshore. But I want to be able to verify that that's the case. So we can actually take a look. We can plot, using this code right here, we can plot the points that were rejected. And of course, overlay them over my observation window. So I think these guys are the drowning deaths, but I'm not sure what's going on along the border. I think where I'm joining the two polygons, there is an inexplicable hole that is teeny tiny that my points are sort of falling through. The reason I'm generally okay with this, it's relatively few points, number one. Number two, I can afford to lose these data that are along the border. I have a ton of data along the border. So I'm not going to be misrepresenting the overall pattern of migrant deaths if I'm missing a couple of points along the border. You know, as far as the drowning deaths go, I am biasing my analysis. I would need to, if I was writing a paper about this, I would need to write as a limitation that I am specifically not going to be accounting for deaths due to drowning. They have to be deaths due to anything else. And trust me, there are plenty of other causes that someone can die from on their way across all this space. Apologies for the macabre. Okay. We do get another warning that our data contain duplicated points. When I was working with the London cholera deaths example, I just went ahead and excluded duplicate points. But I want to point out that there's another way. We have two options. We can either exclude the data, but again, when you're excluding data, especially data as sensitive as this, you're literally excluding people who have perished. I feel there is something ethically wrong with just not analyzing people who have perished. Yes, people who have perished from cholera are still people who have perished, but these are people who have perished in the last 5 years. And so I really want to try hard and include all the data into my analysis. So in this case, just to demonstrate again, maybe another way, I'm not going to remove the duplicates, although I can. I'm limiting the data set at that point. And also, it's not that surprising that there would be near duplicates in where the migrants have died. If there are environmental conditions that cause someone to lose their life, it would make sense that there will be multiple people who lose their life around the same spot, at least numerically speaking. So again, I apologize for the sensitive content, but this is a complicated thing, or I want to relay the complexity of what we're dealing with this data set. So I am a lot more comfortable in this scenario to jitter my coordinates. And jittering is just simply randomly perturbing the X and Y coordinate. I believe it's a draw from a random uniform. So we're just moving the coordinates around by 0.1 kilometers. So that way, we're still representing the overall shape of the pattern, but we hopefully will now not have any duplicated points. And if I do that, I'm going to jitter the X and Y. I'm going to just rename my data set. And now I just get one of the warnings that my points that were technically lying outside of my observation window were excluded. But I still retain quite a few of my points. In fact, I still have out of my original 2315, I still will analyze 2,200 fatal migrant incidents. So I am generally pleased with how I dealt with those duplicated points. See, all this stuff happens before we fit a single model, but I don't have to tell you guys, garbage in, garbage out, correct? So it's very important to take it slow with picking a right observation window, thinking hard about the data points that are excluded, and thinking about how to deal with technically duplicated observations. Okay, exploratory analysis. This is overall a review, but that's okay because we're just about finishing up this unit. There's a lot to do. I mentioned earlier that the book on point pattern analysis has 700 pages in it, but we're an intro to stats class. So I want to introduce you to the third type of spatial data. So I unfortunately have to bring this unit to a close, but it's a good opportunity to sort of review what we've done. So exploratory analysis of intensity, we can make a kernel density estimate. Remember what we do. We think of it as we're putting a piece of chocolate on every single data point that we observe. Piece of chocolate on every single data point that we observe. And then we apply some amount of heat to the chocolate to melt it down. The amount of heat is represented by this sigma parameter. And of course, its units are weird. I think this is larger than the previous example, but also we're modeling a larger data set. So it would make sense, it would take more heat to melt it down. It's a good idea to start by estimating sigma. So this is what this function in here does. It estimates a sigma. So using maximum likelihood that we've seen in a previous example. In my experience, this often has to be adjusted, but you at least have an order of magnitude in which to play with. So I took a look at what my estimated sigma was, and then I included it in here, and I made it larger. So when I take a look at my estimated, sort of my first pass, it picks off the sort of the border crossings around Arizona and around Texas. In fact, I'm seeing 3 separate border crossings in Texas. I'm not sure, but notice that it picks up nothing else. We certainly have data in Mexico and across Central America, but the density around the US-Mexico border is so large that the other sort of pieces of chocolate sort of melt down. And on the scale of the entire data set, we don't see anything anywhere else, even though the data is there. But the estimated sort of intensity is quite low. I made a judgment call to increase This sigma, I played around with a lot of different multipliers. I also played around with making it smaller, where, you know, it doesn't look as good. I think this looks better. It picks off the larger sort of areas of risk for migrants that I think sort of better reflects what's going on around the border. I'm not sure that in the exploratory sense, we should be separating the three sort of crossings in Texas. So my judgment call was to increase sigma, which would cause my, you know, little pieces of chocolate to melt down a little bit further in a statistical sense. And if you make your sigma even smaller, it doesn't look good at all. Okay, moving on. We discussed other types of exploratory analysis. The Fry plot plots the distance vectors within a certain maximum distance. And if they are all sort of clustered together with around small distances, around 0, 0, we have evidence of clustering. If, as we've seen with Chernobyl villages, there are very few small distances, that's evidence of a regular point pattern where points sort of repel each other. So here we clearly have a clustered, you know, a strong evidence that we have a clustered point pattern. We have a lot of small distances. Notice that we're sort of have this sort of a directional pattern occurring. And I think the directional pattern picks up the fact that our window is sort of oriented along this northwest, southeast direction. But again, this Fry plot has strong clustering evidence. We can look at a K function, which compares, you know, our expected number of neighbors under complete spatial randomness and how many neighboring points we observe within some radius. And we see that we are above the complete spatial randomness curve, which indicates clustering again. Did we really need to run this type of exploratory analysis? No. It's pretty clear that this is a clustered pattern. If I was writing a paper about this, I wouldn't really perform these analyses. I would just, it's uncontroversial to claim that migrant deaths are clustered together. They're more likely to occur near one another than far apart from one another. And they're certainly not spatially random. All right. It's time for us to fit a first model. And we flip into R. We have now removed the duplicates, we've performed some exploratory analysis. The next thing we have to do is fit a quadrature scheme. And you guys know what this is going to do. It's going to fill my entire observation window with dummy points, and it will append my observed data locations with that data set, make Dirichlet tiles, and weigh the dummy points and the observed points according to the area of each tile. Now notice I'm specifically showing you how long this takes to run because, again, we're now filling our entire giant observation window with a grid of 100 by 100 dummy points. And then we're going to plot it. It's going to wait a little while longer. I suppose I didn't have to rerun this because all the models are pre-ran. But I can flip back and show you where we're going to use it. Once I get my quadrature scheme, I will use it right here. And all of my covariates go after the comma and the tilde to the right of that quadrature scheme. All right, there it is. You notice that I started with Northern California, and I went all the way down to the tip of Panama. I filled all of my space with dummy points, and my observations are represented as crosses. So this right here is my quadrature scheme. The model fitting, though, is pretty quick because, again, there's no variance covariance matrix to invert. Those of you who were working on the homework noticed that the models ran for a few minutes. A few minutes is quite fast for a spatial analysis, by the way. But there's no variance covariance matrix to invert. There is no multivariate normal distribution to compute. The Poisson is a pretty fast model to estimate. And so the models are going to run pretty quickly. Right there is my very, very bad prediction. Notice all I've used just to give me a start, I'm not even calling this model 1, I'm calling this model 0. I've used a spatial trend of my eastings and northings and the interaction between them. And this gave me the following predicted intensity. I don't intend to believe what this says, but I can look at my residuals to sort of see what I'm missing. Where am I missing? Where am I missing locations that are occurring that my very, very overly simplistic model is not picking up? So if we take a look at these residuals, they are the Pearson residuals. And notice what my standard deviation of the smooth residuals is. It is 3 zeros, 4. Here is the range of my residuals. If you think of this in terms of a z-score, we're looking at a pretty large z-score. Think of dividing this number by this number. It's going to be on the order of thousands. So this, in all indications, is a terrible model. But it does point us, I already maximized it. It does point us to, first of all, around the US-Mexico border, and specifically to the areas around California and Arizona, and extreme eastern Texas along the coast here. And interestingly, we also have this sort of cluster of points in Panama that will be a thorn in my side as I continue building these models. So we know we need to introduce extra covariates into the model. We know the border of US and Mexico is going to play a part. So let's see how it plays out. Moving on. In addition to the distance from US-Mexico border, I'm going to introduce a terrain variable. Now, we can actually go ahead and, sorry, I'm flipping a bit. We can take a look in this viewer about what's going on as we get closer to the US-Mexico border. Look at the topographic map. This is pretty rough terrain. So we have migrant deaths around, where migrants tend to go, but also where conditions are such that unfortunately they die. There are not a ton of migrant deaths here because the terrain is quite rough. There's not a ton of anything. This is a mix of desert and rough terrain that is hard to walk over, or even there. And there was even very few roads to drive over. So terrain needs to be a covariate in addition to distance from the US-Mexico border. So how do we introduce spatial covariates? We can do that with raster files. So here is a raster file of elevation that we can use because it's defined for the entire observation window. We can introduce it as a covariate in my model. Now, of course, I'm going to use R to pull down my elevation raster. I think I've shown you this package before, this elevator package. I simply can run this command to get the raster for elevation across the entire window, the entire set of polygons, the polygons that include all the way from California down to Panama. This takes a few minutes to run. That's why I'm not going to run it right here, right now. But once you run this, it simply pulls down a nice and beautiful raster image. We see there is some really high elevation in the central part of Mexico here. Of course, there's high elevation around New Mexico and parts of Arizona, and of course, California down here. But it also picks out the relatively low-lying and flat areas that we saw quite a bit of migrant deaths here in eastern or southeastern Texas and around here in extreme southern California and the southwestern Arizona. In addition to elevation, if the elevation is high but it's flat, I think it's easier to migrate across that landscape. Luckily, we have a number of tools available to us. For example, using the raster package, I can compute the slope. So think of it as the difference in elevation pretty easily. And I can just plot the slope now to show you that it looks pretty different. This now looks pretty different because, of course, it's picking up the difference in elevation. So this will pick up, hopefully, a different set of spatial patterns. In fact, we see that the slope in most of Texas is near zero, so it's easier to migrate across that land. Roads and railroads tend to be put through spaces that are relatively flat. They get put through valleys, not peaks. So I would believe that this is an important covariate. I need to rescale everything into kilometers, and I need to make sure that I am treating it as an image object for StatStat's sake. So with that in mind, I am now ready to put them into my model. I'm going to keep my spatial coordinate trend and add my elevation covariate centered in scale and my slope covariate centered in scale. This is going to improve my model performance and just avoid computational issues if everything is a z-score. Again, the model will run very quickly, almost deceptively so, but now I have a warning. Now, a warning is not an error, so we have to read what the warning says. It says that our window and our raster files were not sort of aligned. So the raster files were undefined at 0.65%, 30 out of 4,500 quadrature points. That means there were small misalignments between maybe it occurred in the tips of the extreme northern California. Maybe it occurred in and around Texas. Maybe it occurred around Panama and Costa Rica. Remember that we put a quadrature point in every corner, and then we fill the interior with 100 by 100 grid. So just in about 0.5% of those quadrature points, my raster was undefined. If this was a large number, that would give me pause. But because this is such a small number, I'm not worried. I'm not worried about it. So let's take a look at what this model produces. All right, there's a lot of output when we run the summary command. But if we scroll up, we get the estimates on the log scale. Remember, we're modeling log intensity. So I am now on this slide. Just as a reminder, log intensity is our intercept plus, in this case, beta 1x plus beta 2y, and pretend they're centered and scaled, plus et cetera, my elevation and my slope, where the coordinates have been transformed into kilometers to accommodate what I did with my point patterns. Okay, everything is statistically significant, but again, from regression class, the intuition is for a large data set, everything will be significant. So you have to sort of take a look at the standardized coefficient, our coefficient divided by standard error, to see what's really important. Intercept is not particularly interpretable. I don't care much about the coordinates themselves. I care more about elevation and slope, but we see that the z-score is like 18 or negative 18 or negative 17. These are important covariates. Interesting that slope reduces the intensity of migrant deaths because the migrants tend to avoid areas they can't migrate over. High elevation also reduces the intensity of migrant deaths, but you can see that the coefficient is about half that of slope. So it's important when you're using elevation to also consider sort of functions of elevation, such as slope, or there's even a roughness function that I'm not showing this time around. Okay. I can make a prediction, and in this case, I'm overlaying the observed data over it. So we're not seeing, but we are seeing that the model is picking up certain areas. It's picking up, for example, the Central Valley of California as a place where we should be seeing migrant deaths, but we're not. The reason it's picking that up is because of that negative coefficient between elevation and intensity. We model the entire observation window. We don't model only the points. So the model says we should be observing migrant deaths inside the Central Valley, but of course we're not. We should be observing migrant deaths along this, I think it's Baja coast, and we're not. We should be observing migrant deaths along this coast, and we're not. So we're missing something there. And if we take a look at what the residuals are showing, take a look at what the residuals are showing, they will continue to indicate I need to somehow consider proximity to the US-Mexico border. The US-Mexico border kind of goes in a southeast-northwest direction, and it will sort of cut my observation window right over here. So I hope that after I include the US-Mexico border, things will get better for me. So let me do that. There are a few complexities here. First of all, I get it from a shapefile. I have to make sure that it's projected exactly the same way as everything else. And I do it this way. Notice I'm just grabbing the coordinate reference system from my window polygon, and I'm assigning it to my US-Mexico border. And I finally also have to make sure that I carry the entire observation window with me, not just the line, right? The line is one-dimensional, but I have to worry about the area. I have to make sure that I carry all of my US territory, all of my Mexico territory, and the line between them. And that's what the code on line 170 does. So all together now, run this, and I get what I think I should be getting. Along the way, there's some complicated nested geospatial coding that occurs. We always have to plot the results to make sure that we're picking up what we think we're picking up. I have this entire window. I have projected everything the same way, and the US-Mexico border is where I expect it to be. Now, me to find distances, I have to turn it into a so-called line segment pattern, and that's what this function right here does. And again, I rescale everything from meters into kilometers. Seeing what this outputs, it's a planar line segment. Apparently that line is made up of 747 tiny line segments. And finally, you guys have seen this dist map function before. So I will find the distances from the border to every point inside of my observation window. And again, check it out to make sure I'm getting what I think I'm getting. So here was my border object. Right near it, of course, the distance is 0. And right here, down here in Panama, we are almost 3,000 kilometers away from the nearest point of the US-Mexico border. All right. I can now go ahead and include it, centered and scaled, into yet another model. Run the model. It will run quickly. It will still give me my little warning that a few of my quadrature points haven't lined up. But notice that, again, we're not talking about a large number, 32 out of over 4,000, over 4,500. That does not bother me that much. It's, it has to do with the placement of the quadrature points. I'm not too upset with that. If I scroll up here, after including the distance from the US-Mexico border, it has the, outside of the intercept, it has the largest absolute value, Z value, right? You think of this as a standardized coefficient. It is the most important covariate in explaining the pattern of migrant deaths in this observation window. This is a huge coefficient compared to the others. And it looks like it makes elevation by itself, not significant. Slope, however, remains significant. So areas that have a high slope tend to have fewer migrant deaths per square kilometer. As we get farther away from the US-Mexico border, the intensity of migrant deaths falls. The expected number of migrant deaths per square kilometer decreases pretty quickly as we get farther away from the US-Mexico border. All right, let's take a look at this model. All right, we're getting a more believable prediction of risk, prediction of intensity of migrant deaths per square kilometer. We're now really focusing in on the southwestern Arizona and southern California, and we're focusing in on extreme southern Texas, and of course the appropriate northern Mexican regions that border those areas. We're also, if you look very, very closely, have also picked off this little portion of Texas as an area of elevated intensity. And I think it's a real good upstanding model. I included a super important covariate. I think I'm doing a good job. Well, take a look at my residuals, excuse me. And frustratingly, although things have gotten better for me around northern Mexico, around my portion of the United States that I was looking at, maybe even central Mexico, maybe even through right here in central Mexico, I still am having trouble down over here. Down in this area over here. Residuals are observed minus expected. There was a greater intensity. There were more observed migrant deaths per square kilometer than my model was able to accommodate. So it's natural for me to sort of go back to my interactive map and try to figure out what's going on there. Well, let's scroll down. And it looks like it's this cluster of points. I will not pronounce this name. Even if I practiced it for an hour, I would not do a good job. But it appears that it's this cluster of points. It's this cluster of points that is giving me trouble. And now, I spent quite a bit of time looking for a shapefile of the Mexican border with Guatemala. I was not able to find it. I was able to find the shapefile for the US-Mexico border. I was not able to find the shapefile for the Mexico-Guatemala border. So I couldn't apply the same trick. So I chose a different approach. If you zoom in, we have a town of, apparently I'm losing my voice. Too much talking today. I have a town of Tapachula, and I looked up the coordinates of Tapachula. I project them as first lat long, and then I reproject them as in universal transmercator, zone 13, just like the rest of our data. I have to make a point pattern object. Again, the coordinates get further transformed from meters into kilometers. And I'm thinking I'm going to fix everything with the distance from the town of Tapachula. Again, just take a look. Yeah, this looks like it's picking off the problematic area that my model can't explain. So I think when I include the distance from Tapachula, which serves as a proxy for the border of Mexico and Guatemala, hopefully, along with the US-Mexico border, things are going to be better for me. Here is model 3. So model 3, I try to get competitive. And I said, man, this is such an important data set. I really want to do a good job here. But lo and behold, I sort of failed. I pulled out all the stops. I must have run 20 different models. They run pretty quickly. So you too can run 20 different models if you like. But I included the distance from Tapachula, quadratic function of my coordinates, right? There's my quadratic function of my X and Y coordinates and their interactions. So I also added an assortment of uninterpretable interactions. Should I have done that? I was trying to be competitive with R. I was trying to be competitive with point pattern analysis. So I was just trying to do the best I could. So, maybe do as I say, not as I do. Don't randomly add an assortment of uninterpretable interactions, but I'm trying to show you that I did the best I could, and I am still not doing a good job in the same darn area where I tried to do a good job with adding my distance to Tapachula. I also am including the interaction between the border, the distance between the US-Mexican border and distance from Tapachula. Look, all of this stuff runs quickly. The model is even mildly interpretable. This interaction of US-Mexico border distance and distance from Tapachula has a negative coefficient, which means that as we get farther away from both the US-Mexico border and the town of Tapachula, intensity decreases. That's realistic. Whereas my interactive map. As we get farther away from the US-Mexico border in the north and the town of Tapachula in the southeast, the intensity tends to decrease. I follow that. But when it's all said and done, I still failed in explaining the one cluster I came to explain. And it did make me sort of really upset. At this point, it's fair to ask, well, I did all I could, but could our unexplained cluster of migrant deaths be treated as a finding? The model fits pretty well everywhere else. Let's look at a blown up residuals map. My model fits well enough in a lot of other places. Certainly around the US-Mexico border, certainly around the northern Mexico region, even down here in maybe Costa Rica and Panama, things fit pretty well. I'm just failing to explain this cluster. If I go back to my interactive now, I'm failing to explain this cluster of points. Maybe those are rail lines that I'm missing. So I'm missing distance from a rail line. Maybe those are major Mexican freeways that I'm missing the distance from those. In fact, these are very linear patterns. That's why I'm thinking, man, is there a railroad there? But I have to be very careful. If I include distance from railroads, I have to include distance from railroads everywhere in my observation window. So I have to be careful when I do that. So in short, I hope that my mistakes were informative to you, or this analysis was informative to you in how you would approach modeling a complicated data set across a very large area. Is Model 3 the best model? Well, according to AIC, sure, it is. Maybe it was a mistake to include all of California. Maybe if I included only the 100-kilometer buffer of the California that's near the US-Mexico border, I could have done better. Maybe we should have used only the high-quality sources from my original Missing Migrants data set. I don't know. All of those are possible ways to improve. Sort of to conclude this unit and this lecture. Statistical modeling in general is a cyclic process. We fit a model, we critique the model, we consider how we can improve, and then we repeat. So we are considering how to improve on my last model, Model 3, which is better than all the previous models, but it's certainly not perfect. I think we have to consider all models are wrong and some are useful. Did we make a useful model? Well, it ticks off the areas around the US-Mexico border where there is high intensity of migrant fatalities. Is that a useful model? And this is where I would be hard pressed if I didn't mention ethics. I don't think it's that hard to see. If you want to help migrants, you can use this map to figure out where to go to help people. If you are trying to hurt migrants, you can use exactly the same map to go and hurt people. So I think as soon as you introduce location of a person into a statistical model, we absolutely must consider the ethical implications of what we're doing and what we will be using this model for. Was it important for us to find out that elevation doesn't matter, but slope does? Maybe that could have been intuitively figured out. But now we have statistics to show that's the case. So I don't know if we made a useful model. If I'm trying to help people, then I would be maybe leaving water and food around this tip of Texas and around this border areas in Arizona. Maybe they're all well known. So maybe the whole point of the analysis is this unexplained cluster down here in this region of Mexico. There are more migrant deaths there than can be accounted for by this model, which fits pretty well everywhere else. So there's something happening there, and we're not sure what it is. Modeling across big, large areas is tough because I think the relationships between our covariates change across space. Why should we assume that the relationship between slope and intensity of migrant deaths remains constant as we cover a quarter of the globe? As we get closer to the equator, it's warmer at higher elevations. As we get farther away from the equator, it's colder at high elevations. Am I missing some crazy four-way interaction here between the y coordinate, slope, elevation, and distance from Tapachula, Mexico? It's possible. It's possible I'm missing some high order interaction that might explain how the relationship between our outcome and the covariates vary in space. But it's hard to come up with that exact functional form. And of course, it's difficult to know whether our large residuals are a finding, that there is something going on there, or it's due to my poor modeling choices. So with that, let me close this hopefully informative analysis of the super important sensitive data. You guys have yourselves a safe, restful, hopefully restful weekend. We will have an activity on point patterns on Tuesday, and then move on to our last type of spatial data for the semester. We're getting close to the end, guys. And of course, your final project will be due at the end of the semester, and I want to give you time to work on the final project, because I think that's when you really put everything together, and hopefully everyone does a good job. All right, thank you guys so much for your attention, and I will talk to you later. Bye-bye.